Someday, I hope they let me teach complex analysis. Algebra gets boring. I think they only let very senior people teach complex analysis. It's kind of a reward for long service. Start. So we'll talk more about complexes today. So I'll introduce some new constructions and also try to motivate them in terms of topology. So we'll talk about double complexes. Tensor product of complexes, and hom of complexes. So let me just start with the definition. So we're going to work inside the category of R modules. And we know what a complex is. It's a sequence of R modules with R linear differentials. And one often encounters the following kind of situation. So a double complex of R modules consists of the following kind of data. So it's a grid of modules, and in which each row and each column is a complex. So this is 0th row. This is first row. And so on. Our convention is that differential is lower degree. Maybe it goes on forever in all directions. Maybe it's eventually 0 somewhere. So I'll label the differentials like this. I'll label the differentials by the source, just for concreteness. This is 0, 0, 1, 0, and so on. So in which, a double complex is a grid like this, a grid of modules and maps in which each row and column is a complex and the squares commute. So if I do this differential, then this one is the same as this vertical one, then the horizontal one. And there are two ways. Well, actually, let me give two examples. And then I'll tell you, once we have the examples, what we'll do with them. So eventually we want to make single complexes out of a double complex, and there are two ways to do that. One involving a direct sum and one involving a direct product. So example would be, suppose R was commutative. For simplicity, let's say it's just the integers or some other commutative ring. And then we know how to take tensor products of modules, right? So given two complexes, let's say x dot and y dot, okay, we can form a double complex which looks like the following. I put the 0th term, tensor product, the 0th term at 0, 0. I'll let the differential act in the first variable of the tensor product, in the horizontal direction, and in the vertical direction. Let's see. I see. That's a little unfortunate from the way I've written it here. So I'm letting the first one. Right. Okay, so what is this? This is id dy. And in this direction, this will be dx tensor id. So on the first factor, it's dx. On the second factor, it's id. And this would be what? X minus 1, y minus 1. So this would be id dy. And this would be dx id y, and so on. And then you can figure out what the other terms are. So incoming here would be x0 tensor y1. Incoming here would be x1 tensor y0. Okay, so that's kind of example 1 of a double complex. And the squares, so the rows commute, because if I do id tensor dy followed by id tensor dy, I get id tensor dy squared. And similarly, in the vertical direction, I'll get dx squared tensor id for the composite. So the rows and columns are complexes, and the squares commute, because if I'm computing the composite of tensor products of maps, it's the tensor product of the maps. Who knows what a tensor product of modules is? Who knows what a tensor product of modules is over a commutative ring? Okay. So this is important. It should be in a basic algebra class. If you don't know it, you'll have to learn it. If you need help, come and talk to me. Okay, so here's the same situation of two complexes. But now instead of tensoring them together, we're going to make Hom. So in degree 0, I'll look at Hom from x0 to y0. So this will be over whatever the ground ring is. I can compose that with the differential in y. So this would be a map from x0 to y0 followed by the differential in y. Here, I could pre-compose with the differential in x. Okay, the differential in x goes from x1 to x0. So this will take me from a map that goes from x0 to y0 to a map that goes from x1 to y0. This will be post-composition with dy. this will be precomposition with dx. And I do this in all degrees. So if I go along the rows, I'm going to be postcomposing with dy twice, so that will be 0. If I go along the columns, I'm precomposing with dx twice, so that's also 0. So rows and columns are indeed complexes. And this commutes because what is it in a square? If I have a map, it says send that map to f precomposed with dx, postcomposed with dy, or postcomposed with dy, precomposed with dx. Okay? And so by associativity of compositive maps, this commutes. Okay, so this is called the Hom underline double complex. So these are probably the two most important double complexes. And what do we do with double complexes? There are two ways to make them into single complexes. There are two ways to make a double complex into a single complex. So both of them involve looking at a diagonal. Okay? So you look at the diagonal where the indices all add up to the same number. So on this diagonal, everything adds up to 0. 0 plus 0, 1 plus minus 1. On this diagonal, everything adds up to 1, and so on. Okay? So, so given a double complex, x dot dot tot plus of that I'm going to tell you what it is in some degree, and then I'm going to tell you what the differential is. So it's in degree, let's say, k. It's the sum over the diagonal where everything adds up to k. I comma j, I plus j equals k. Okay. That's the definition of the kth term of this double complex. And the differential so the source of the differential is a sum, right? So I just have to tell you what the co-components are. I have to tell you what it is on each summand. So with differential restricted to x I comma j, so on that summand, the differential is going to be a difference of differentials. Okay, so let's see. I'm going to raise in one direction, lower, sorry, in one direction and lower in the other direction. And I have to choose a convention about kind of whether I want to change signs in the rows or in the columns. So I think I'm going to change it in the columns. So the way this will go, the differential in the column that preserves the column is this. So I'm going to let this be minus 1 to the I. I see. Do I have a bit of a problem here in the way I name things? Yeah, so I need to give them names, right? because this would also be d0, 0. So I need to talk about vertical and horizontal. This is horizontal, and this is horizontal, this is vertical, this is vertical. Okay? So this one here, it lowers the index of the row, so that's a vertical one. This will be dv vertical, ij, minus 1 to the I. Actually, I probably want to number it by the column. Yeah, let's number it by the column. So a j plus, in the horizontal direction, nothing will change. It will just be the horizontal differential. Okay. And you can check, and we'll see it in examples. You can check that because of the signs, this thing that's supposed to be a differential squares to 0. We'll do an example in a second. Let me tell you what to do with the other construction. It's very similar, except we use a product instead of a sum. Okay, so we also have tot product So in degree k, that's just going to be almost the same thing, but now it's a product. And so if the diagonal along which we're taking the product has infinitely many non-zero terms, that's going to be different, not isomorphic to the sum. Okay. With differential, so now the target of the differential is a product, and so I just have to tell you what all the components are. Here I told you co-components because the source was the sum. So with component of differential, given as, so okay, so what do I have? I have a product over the diagonal where everything sums up to k. Right. How do I want to say this? Just a sec. Okay, so suppose the target is xij. That's one component where I plus j equals k minus 1. Then at that point in the double complex, there are two incoming things where I raise I by 1 or I raise j by 1. Okay? So this map here is a sum. Well, it's going to be a difference with a sign. So I will project onto xi plus 1, comma j, cross xi j plus 1. And this will be a sum with a sign of these maps. So this one lowers I, so that's a vertical. Right. So this will be minus 1 to the j d vertical. plus, so it's just like this, d horizontal. Okay. And for the same reason as this one, you can check because of the signs, this will define a differential. Now let's do two examples, concrete examples. Very concrete. So let's go back, special case of example 1. Let's do example 1. So we can say what it is in general, and then we'll say kind of more in some very special case that's useful what it is. Okay. So by definition, the tensor product of two complexes over a commutative ring is tot plus of the tensor double complex. Okay. So let's think what that means. It looks like in degree 0, it's the sum over tensor products where I plus j equals 0. Going into xi plus xi tensor yj, where that adds up to 1, adds up to minus 1. And similarly here, this should add up to 1, and so on. And how do we compute it? So suppose I'm probably going to change the sign convention. So there's a theorem, which is that it's impossible to get all the signs consistent in homological algebra. And the proof of this theorem is that Pierre Deligne once tried to do it, and he failed. So there's something called sign manifesto, and there are mistakes in it. Okay, so suppose I have an element, x tensor y, in, let's suppose it's xi tensor xj, yj, okay? And so that's in some sum. That's in some sum, say of degree k. That's a sum in there. What is the differential on this? Okay, I want it to be, and I think according to my sign convention it's not quite, I want it to be the following. This is the standard convention. I first apply d to x, and then I tensor with y, and then I move d past x. So this could be plus, there'll be some sign. This sign should be degree of x, which is I, tensor dy. This here, according to the way I've written things, is the vertical differential. And this is the horizontal differential. So here, in these formulas, I actually want the sign to appear, let's see. I want the sign to appear in front of the vertical differential, in front of the horizontal differential. So I should write that. This is minus 1 to the what? It looks like it's the source. Okay, and similarly over here. So plus minus 1. Which one is the horizontal? Horizontal is on J, yes? So it's this, j plus 1. And the horizontal here was what? Horizontal should be in j. So this should be j. Okay? Just a minute. I said I. And now let's do a very specific example. What we have is the algebraic analog of a cylinder. Okay, so very special example. Let I, for an interval, let this be, remember, given a simplicial set, we can form a chain complex, which in each degree is formal linear combinations of the simplices, and the differential is alternating sum of face maps. And that was very big, because there are lots of degenerate simplices. So we factored out the degenerate simplices, and we get this reduced complex. For an interval, this is something very simple as a complex. This is free in degree 0 on one endpoint of the interval, and the other so this is in degree 0, and then in degree 1, the only non-degenerate simplex is the whole interval. And the differential sends the interval to the difference of its endpoints. This is the usual thing in algebraic topology. Okay, so that's a complex. And let's see what happens when we tensor that with some other complex. Okay, so let's compute I, tensor any other complex. So what does this look like? So let's write down the double complex. I'll have, this is I0. This is I1. Yes? So I'll have in degree 0, I'll have this, and this will be two copies of x naught. One for this generator, one for that generator. Differential like this. And the next rows will be 0. And then I'll have an incoming differential in the vertical direction, I1. I0, x minus 1, sorry, I1, and so on. And then there's nothing in degree 2 in the I complex. So we just have two rows like this, but we have as many columns as we have non-zero terms of x. And I want to sum along the diagonals. Like that, and then take the differential with appropriate sums. So let's work this out. So in degree k, what do I have? I have two kinds of terms. I have an I0 tensor xk, plus an I1 tensor xk minus 1. Okay, and so an element here looks like what? I'm going to write it like a column vector. I'll have 0, the element 0 here, tensor an element of xk. I'll call it xk. I'll have an element 1 tensor some other element of xk, xk prime. And I'll have 0, 1, which has degree 1, times something of degree k minus 1, and together they'll have degree k. Okay? And where does the differential send that? Well, I can compute it. It's a sum of these things, so I can compute it on each one. So what is it on here? I apply d to that, but that's 0 because the next term in the interval is 0. Okay? And then I move it past there with a sign, but there's no sign. It's in degree 0. So I'll just get dxk. Okay, so I'll get 0 dxk. Okay. Here, same kind of thing. I'll get 1 dx prime k. And here, what do I get? Now something interesting happens, because when I apply d here, I'll get a difference, right? I'll get 1 xk minus 1 minus, that will be the term with the 0 in it, xk minus 1. And then I'll have to move d past there. So I'll get minus 0, 1 d xk minus 1. Okay? And so let me write that. I wrote it in column as if they're column vectors. Let me write it as a matrix, because there are variations on this which are convenient to write as matrices. So what is it telling me? To write a matrix, I tell you in the first column where the first basis type vector goes, right? So there, it was just acting as d on x and had no other contributions. Here, it was very similar. It was acting as dx. And here, something interesting happened. So here, it was minus the identity plus the identity and minus the differential. Okay? And so you can check that if you put two of those matrices next to each other and multiply them, it squares to 0. Okay, so you can check that this squares to 0. So that's what it looks like in this simple example. We'll see lots more examples as we go along. Let's do the same kind of thing, but for Hom now. Are there any questions about this tensor product of double complexes? So tensor product of complexes, you form a double complex, you sum up the diagonals, and put in the differentials with signs. Okay. So let's look at example 2. We again have two complexes. We form this Hom double complex. It's still there, right there. But now, by definition, the Hom complex between them, let's say I do this over R, by definition, this is total product of the Hom double complex. So maybe my notation for double complexes will be curly braces. I'm leaving the differential in the double complex kind of implicit. this is xi, yj, like this. Okay, so let's compute something. So let's spell out what this looks like. This is in degree 0, they should sum to 0. In degree -1, they should sum to -1. And so on. And I want to think about what would a cocycle for this complex be. Okay, so suppose I had an element here. So for each I, let's see, so it's a collection. I'll write them like this. It's a map from xi to yj. And I want to compute the differential. So it should have a bunch of components. We said what the component should be, yes? So they should be a difference, depending on signs, like this. So let's look at a single source term. Right, I see. Okay. So I think it will be the following. It will be dv. So if I apply dv to fij, what does v do? It raises the index in the source. So this will be a term in I plus 1 comma j. Okay? And there will also be something, a horizontal term, but it won't be from ij. It will be coming in from something that has one higher in the source, in the target. So this will be fij plus 1. And the sign here, so the columns are labeled by the target. So I think I put a j plus 1 here. Okay. What's that? It's a convention. It's a convention. So I think this is the convention which will play well with respect to the tensor product. So this will work. It will give something square 0. A different convention would give something quasi-isomorphic. So let's go with this for a minute, and let's unwind what it means. Okay? So what does it mean? What is a cocycle? Say of degree 0, for simplicity. It means that all these terms are 0, yes? But let's write out what these things look like. So fij is a map from xi to yj. Okay? And so that's fij. What is coming in here? Yj plus 1 is coming in. here I have, very good. This was Fi. Right, I think I got. I think I got this off. Let me write it out explicitly. So this went to hom xi yj minus 1. Yes. And what is coming in here? It's hom xi minus 1. Yj minus 1. I see. Okay. So what we've drawn is correct, but the indices that we wrote in the product were not quite right. Notice what is constant along these diagonals. It's not the sum of the degrees, right? It's the difference. Okay, so this should have been, so that's what was confusing me. This should have been the difference. Right? 0 minus 1, minus 1 minus 0, that difference is constant, not the sum. And the reason there's a sign change is because, I mean, somehow the source and target, one of them is contravariant, one of them is covariant. Okay, so indeed, what should be coming in is this. So this is minus 1, j minus 1. And this should be j minus 1. Okay? So we're looking at the following diagram. And what does this being 0 tell us? It says that the following diagram commutes. That if I put here a sign, then this commutes. Okay. So the cocycle condition says, cocycle condition says up to signs. I need to fix the signs. So I apologize about that. So the cocycle condition says up to signs that this collection of vertical maps, these Fij's, these form a map of complexes like this. Okay. So notice in the terms here, there's nothing about the differential. The differential is only involved in going from here to here, and the fact that something's a cocycle records that this collection of data actually defines a chain map. Okay. So I see now that I didn't get the best convention for the signs. So I will, when I write up the next seminar sheet and type it up, I'll put in the correct signs for reference, okay? Okay, so there are these two constructions. This is what they're used for. And an exercise will be and this will be in a seminar, that tensor product and Hom, like this, are adjoint functors between complexes. See, these, just like usual tensor product and Hom for modules. Okay. So are there any questions about these constructions? Don't ask about the signs, but you can ask about anything else. I'll get the signs right in the seminar sheet. So for tensor product, they're good. For this, I made some mistake in how this is supposed to work. Okay. Okay, so what are we going to do with this? These constructions we'll use over and over again when we talk about ext and tor, which are the basic functors in homological algebra. But I want to use the tensor product in particular with the interval, to motivate the following construction. So I want to first recall a construction from topology. So this will be the so-called mapping cylinder from topology. So given a map of spaces, this is a map of topological spaces, so morphism at top. The mapping cylinder is constructed as follows. You take the cylinder on x, so imagine x, for instance, were a circle, and crossing it with an interval would be a cylinder. Okay, so this is kind of the cylinder on x. And then I want to glue that to y via the map that glues one end of the cylinder to its image in y. So this will be on x. So I'll look at the end of the cylinder, and then I'll apply f to it. That will give me a map to y. So this is a push out. And let me draw a picture of it. So I have x. I have the target space. It has some image of x. I have x included into a cylinder like this, where I've colored the embedding. So it's embedding, if this is from 0 to 1. And then I'm going to glue this end of the cylinder onto here. And so in the end, I'll get a picture that looks like this. Okay, but this is formally what it is. It's this push out. And there's an important analog of this. I'll leave this. There's an important analog of this in homological algebra. And they actually correspond in an appropriate way. Okay. So now let's say mapping cylinder. So definition. Given a map of complexes, like this, from x to y. You imagine they're like topological spaces, and you do an algebraic cylinder where you tensor with the interval. The reason you do that is because if you want to compute chains on the product of two topological spaces, this is homotopy equivalent to the tensor product of the two chains. This is called the Eilenberg-Zilber theorem. We will have an extended exercise about it. So given a map of complexes like this, the mapping cylinder and I'll write sil with a dot to emphasize this is for complexes, it's going to be a push out. So I'll have a map from x to y as before, but I'll embed x into its cylinder, I tensor x. This is the algebraic cylinder from over there. And then I'll form the push out. And I want to compute this push out. I'll give a formula for it. Okay. So what does it look like? When you compute, we saw in the seminar last week, when you compute colimits of a diagram of complexes, on the terms, you compute the colimit at each term. And then the differentials come along for the ride. So if I do this in each term, say in degree n, I'll have a yn here. What is the degree n stuff here? It's I0 tensor xn. There are two terms there. And then there's I1 tensor xn minus 1. Yeah? And one of the xn's gets glued onto the y. So one of the xn's, so let me write it out, cylinder of f in degree n looks as follows. It's xn plus xn minus 1. So this is kind of 0. This is 0, 1 from the cylinder, plus yn. Okay. Now I have to tell you what the differential is. Okay, so let's work it out. To compute a push-out of abelian groups, I can take the co-kernel of the difference of the two maps. So on this term, it will just be D. So I'm going to write it as a matrix. So it will be dx I worked this out carefully this morning. Why is there not what? It's going to, under this, it will get glued to the copy of y. So the formula is the following. This will be id x minus dx and f. So if I apply f here, it will map to here. And then on y, it will be just dy. So you can check that this is square 0. You can also check that it correctly computes this push out. And there are a few things we want to note about it. So note a few things. One is that there's some obvious subcomplexes. The fact that in this column, we have it acting as the differential in that term and then zeros elsewhere, it means that this map, which sends x to x, 0, 0, is an inclusion of complexes. Okay, very good. We also, if we do a similar thing here, we see that y is a subcomplex, but actually it's also a quotient complex. So this is note A. Note B, if I just drop everything and take the y component, this is a surjective map of complexes. Which has a retraction, so y also includes. So with a section, y goes to 0, 0, y. Okay. So the complex y splits off. And what's the difference between them? Kernel of this projection its elements in the complex where the last term is 0. Okay, so that's a subcomplex. It's the kernel of a map of complexes. And I claim that this kernel is exact, and in fact, null homotopic. This kernel is null homotopic. Therefore exact. We saw last time that if I had a null homotopy, then the complex was in particular exact. So it has no homology. So the explicit homotopy is as follows. Let me get it right. So the null homotopy is the following. The only thing that can really go wrong is getting a sign right. So the null homotopy sends an element xn minus 1. I can ignore the 0 term up to isomorphism. So the null homotopy will send this to 0 minus xn. Okay? And you can check using this formula for the differential that this is a null homotopy. So what do we conclude from this? So we conclude, in particular, that the map from the cylinder of F to Y is a quasi-isomorphism. So let me say K is the kernel. the kernel K dot so we have a short exact sequence of complexes like this, where this term is exact. So we, in particular, that from this short exact sequence and the long exact sequence in homology, we conclude that this is a quasi-isomorphism, because there's no homology there, and so in the long exact sequence, all the maps on homology here will be isomorphisms. So this is a surjective quasi-isomorphism. Okay, so what have we done? Let me summarize. This is a construction. Let me summarize the moral of it. So the moral is that given any map of complexes, in general, it's not going to be injective. And so it's not obvious how to get a long exact sequence from it. If it were an injective map, I could take the quotient, I would have a short exact sequence of complexes and a long exact sequence in homology. In general, that's not the case. But we construct a commutative diagram of complexes. Which goes like this. So I have the original map x to y. It is what it is. Maybe it's not injective. I replace y with something quasi-isomorphic, and this surjects onto it. And I also had an inclusion of x into there. Okay. And now, because this is an inclusion, I can take the co-kernel. So I don't know, let me call this f tilde. So this is the co-kernel of this f tilde. It has a name. We'll compute what it looks like in a second. It's called the cone. And this is the notation. This is called the cone of f. The name also comes from topology. It corresponds to taking that picture, which we erased, and pinching one end of the cylinder. Okay, so this was not an inclusion, but we replaced it with something which, up to homology, is really the same and is an inclusion. And once we have that, we can take the co-kernel to get a short exact sequence. And this is a construction that people do in topology and also works in this context of homological algebra. So if you've seen homotopy cofiber in topology, this is how you compute it in terms of a mapping cylinder. Okay. So we get now a long exact sequence in homology. Which looks as follows. So I have hi of x mapping to hi of the cylinder, which is just, because of this quasi-isomorphism, hi of y. And it's easy to check because this commutes, that that's the same map you would get just from F. But now I have a new term. This is hi of the cone, like this. Okay? And then it continues. This is hi minus 1 of x. This is hi plus 1 of the cone, and so on. Okay? So this is a natural way to take any map of complexes, replace it by something which at the homology level is the same, but is an inclusion, and get a long exact sequence. And one thing you might worry about is that suppose the original map, x to y, was already an inclusion. Then I know how to make a short exact sequence of complexes and a short, long exact sequence of homology. Is that the same as this one? And they are. So note, if this map here is an inclusion, then we have a short exact sequence of complexes let's call it y mod the subcomplex x. Let's call that z. Okay. And its own long exact sequence. And we might worry that this is different from the thing we've just constructed. But we don't need to worry. So we can compare these two things. So I have the inclusion of x into y. I have the quotient z. Above this, I have the inclusion into cylinder of f. And I have the cone. And because this is the co-kernel of this, and this is the co-kernel of that, and this commutes, we get a map here. A unique map making this commute. Okay? And now you can check. This is an equality, so it's an isomorphism on homology. This is a quasi-isomorphism. It's also an isomorphism on homology. And then here we have some maps on homology that we don't understand yet. But you can check those maps are sandwiched between isomorphisms on either side. So you can check that this map is also a quasi-isomorphism, because we get a map between two long exact sequences in which we already have isomorphisms on either side of these maps. So I'll have a map from hi of the cone to hi of z. In the long exact sequences, on either side, I'll have isomorphisms, and this will be forced to be an isomorphism. Okay, so we get an isomorphism of long exact sequences. So this is the natural way to take any map of complexes and up to quasi-isomorphism, make it into an inclusion, followed by a quotient, and get a long exact sequence. So are there any questions about this construction? Yes, you could say it like that, or even if you didn't know the 5 lemma, you could just think about my claim. This is a very special case of the 5 lemma. Very good. Okay, so we had this cone. I defined it as the co-kernel of this inclusion of x into the mapping cylinder. Let's compute what this cone is, because it's nice to have a formula for it. So let's compute the cone. So what do? We factored out one factor of one component of x. And so what are we left with? Where was our formula for the cylinder? Did it looks like I wiped it out. Okay. Well, let me write it again. We have the cylinder in degree n. This was xn plus xn minus 1 plus yn. And we have xn. It's including into that summand. So we're just going to quotient that out. So the nth term here is going to be xn minus 1 plus yn. And then we should spell out what the differential is. Okay. And the differential on here. Well, we had a formula for the differential in the cylinder as a 3×3 matrix. We just take out the first row and column because we killed xn. So it will look like this: minus dx f 0 dy. Okay. And so it's often, if you want to compute what this map looks like, it's often convenient to use the section. We said that there was a section where the first two x terms are 0, and then map like this. Okay? And so this is just the inclusion of y as a subcomplex here. So note we have an inclusion of complexes like this. That's a subcomplex. And this gives the desired map for our long exact sequence. In this, I'm going to call it canonical because we saw it didn't really depend upon the two ways to construct it. Defined by f. Okay, so that's a useful calculation. And it's worth doing a few very simple examples. Right. So let me do a very simple example, partly just to practice the definition, partly because this actually has some meaning. So suppose I start with some complex x. And suppose the complex to which it's mapping is just the 0 complex. Okay? then what does the cone look like? Well, let's write the cylinder. Then the cylinder, so I don't know, I'll call this 0. Then cylinder of 0 in degree n looks like xn plus xn minus 1. But we know, in fact, that it's quasi-isomorphic to y, which is 0. So this is exact. In fact, I think it's null homotopic. I think you can write down a specific null homotopy. And what is the cone? So cone of 0. Remember, I factor out this first component, so I'm left with this. So in degree n, it's not xn, it's xn minus 1. And what is the differential? I see. Yes, just a minute. Yes, it's this right here. Right? This is the xn minus 1 component. It's this with differential minus dx. Okay. So, in fact, this defines what's called the suspension of a complex. It's related to the suspension in topology. So definition, given a complex x dot, its suspension so the topological notation would be like this. Its suspension is the complex which in degree n is xn minus 1, and the differential has picked up a sign. So this is just a definition. It looks very innocuous, but it's very important. And I want to make a warning about notation. So I'm introducing suspension because this is unambiguous. Unfortunately, in some sources, mostly written by algebraists who don't know any topology, they're very confused about the notation for this. So some people will write it x square brackets 1. Some people will write it, which is correct. And some people will write it x square brackets minus 1. In particular, Weibel does that. And this is a big no-no. But to be unambiguous, I'm going to write it as a sigma. Okay? So, so the correct notation, I mean, it's a convention, but I think it's correct by majority rule. So the correct algebraic notation should be x square brackets 1 but Weibel and maybe some other sources, Weibel writes x square brackets minus 1, and this is really offensive. I don't want to see this from you. Okay, so we'll stop there. That's a bunch of constructions with complexes, the canonical way to make a long exact sequence from a map of complexes. there's the inverse of this, which is shifting the other way. And so I can put that on the board right now. It also has a topological meaning, but I don't have time to motivate the topological meaning right now. So there's inversely, there's what's called loops x. Has the following. So it's the opposite. This is xn plus 1 with differential also a sign. Minus dx. And obviously these are inverse. The two signs cancel out. And the correct algebraic notation is x dot shifted by minus 1. Okay? And so with this notation, you can check the following. And then I really will stop. You have a map of complexes. You have the cylinder on F. So this. Then we take the cone. Like this. And if you look at this composite map, we saw that y included into the cone. And if you take the quotient of the cone by y, you'll find the suspension of x. Okay? And you also get a long exact sequence for that, and it will just be the shift of the 1 from here. Okay. So let's stop there. Any more questions? Okay. Just a sec. So we have a minute. So the question is, why is it the suspension? If you look at the cone, it had two terms, right? Xn minus 1 and Yn. I'm factoring out Yn, so all I'm left with is Xn minus 1. That's the nth term of the suspension. And what is the differential after I factor out this term? It's that.